Hello there. My name is Howard Changhao Tai, and today I'm going to be presenting graph neural networks and rock climbing classification. So specifically, the problem that is being solved is determining the difficulty of a climbing route that is on a MoonBoard apparatus. Now, what is a MoonBoard? If you focus your attention to the lower left-hand side of this poster, you'll see an image of a MoonBoard canvas. And essentially what a MoonBoard is that it's a modular climbing wall of fixed dimensions. There's exactly 18 rows and 11 columns. And the problems set on it range in difficulty from a V4 to a V14. Now we're taking a graph-based approach to solving this problem. And what is a graph? Essentially, it's a data structure whereby the individual elements are represented as nodes, and the relationships among these entities are edges between these nodes. And these MoonBoard problems are directly able to be represented as a graph. And essentially, we can specify nodes on these graphs to be, say a specific problem, and also specific nodes. So here we see a schematic of a graph. And in this particular case, this is actually a schematic from text GCN, which is where we draw a lot of our inspiration. And document nodes are shown as colored. Word nodes are shown as uncolored. And essentially, for our particular case, document nodes are problem nodes. Word nodes are hold nodes. And essentially, we can create a graph convolutional network that operates on this graph. And exactly what is a graph convolutional network? Well, right here, where my cursor is pointing, is the forward pass equation of a graph convolutional network. And essentially, at every single step of a graph convolution, which is defined by a matrix multiplication between A tilde, what essentially happens is that every single node has access to information from of nodes that are one hop away. At 2 steps, every single node has access to information 2 hops away, so on and so forth. And essentially, for a graph classification task, we use a modified version of the cross entropy loss function that really only takes into consideration the loss from labeled nodes, because not all these nodes are going to be labeled. Some are going to be holds, and some are going to be problems. Now, we ran a total of 17 different experiments. In these 17 experiments, we aim to benchmark the graph convolutional network with baseline statistical models, as well as other neural network implementations, like the fully connected network, so on and so forth. All in all, we found that graph convolutional networks performed the best, actually, by far. The best experiment is outlined here below in red, with a AUC score of 0.73 and an average F1 score of 0.31. We also found that GCNs were more stable to essentially data imbalance, and really they produced better predictions across the spectrum of the difficulty classes. All right, thank you very much for listening to my presentation, and this is it.